Hello. Now we go for the solution. Okay, we're going to implement our interior point method. That was discussed, this paper was discussed in the previous video, and now we have the solution here. Of course, I'm going to open up and explain the details on this. Let me increase size here. Sorry, guys. Just make it like this. I think it's to be easier to see. Okay, so let's go for it. First of all, I just decided to write several functions here, but I will discuss on top of this. Test simple data set. This is my necessary function. It's going to call another function called simple data set. Let's see this function. See what happens here. I just decided to create a training and a test set. Okay, the training set will be formed by a bidimensional Gaussian function. So I'm concatenating in terms of columns, and then I concatenate in rows another Gaussian. This first Gaussian has the mean 0, 0, and this second has the mean 10, 10 by dimension. The first 100 elements will belong to the negative class, as you can see here, and the next 100 to the positive class, as you might notice here. Test. I just synthetically generate elements with the mean 0, 0 and with the mean 10, 10. And I decided to generate 10 elements each, 10 belonging to the negative class and 10 belonging to the positive class. And then I return this in a list with my train and my test sets. Okay, quite simple. I take data set train columns 1 and 2 to compose my input space X. So this is my input space. My output space or class labels are defined in terms of my third column of the train. Okay, I just defined it as a vector, a column vector. My y is a column vector. Here I just said, okay, the number of points I have in X is, in this case, 200, as I discussed with you guys. So how can I compute my Q matrix? Y product by transpose of Y, element-wise multiplication by X multiplied by X transpose. That's my Q, as we discussed before. I just decided to define some value for my cost, could be greater, but I used a 2 here. I defined some eta. We are going to discuss on eta later. This is me. That's the relevance I'm going to give to the barrier. I set up my initial B as 1. The number of iterations we have, I'm going to start with 1 and then increase. Some gap, some threshold for our gap, just to decide when to stop running. Okay, I think you guys remember that from the previous problem. A vector of ones, that vector is going to have 200 ones. Take a look, any row is 200. Repeat 1 for 200 times. My diagonal matrix with ones, number of elements, 200. Repeat those 200 elements and transform them into a diagonal matrix. That's my identity matrix. Going down, going down, going down. Here I have some initial alpha vector. I just decide to define alpha is equals to 0.1. That's greater than 0, as you guys know. We discussed about that. I'm going to go to the end. Discussed about that here, the previous video. I need to define some initial solution for alpha in alpha greater than or equal to 0. I decide to define a 0.1. Then this guy alpha is going to be my diagonal matrix used in my calculus. Okay. Here to make sure that we ensure all those values, I just made psi equals to my alpha vector 2. That's a way of, I just decided, okay, I'm going to initialize psi I as something positive as well. So psi i's have to be greater than or equal to 0. And then I computed my matrix S. Sorry for calling it like S1 here, but it could be just S, guys, sorry. But I just decided to call like S1. Could be S, sorry. Here, I computed S, as you might see. I did my psi minus by q multiplied by alpha minus e. That's actually this guy over here, making it equal to S, right? That's how, let me show like this. That's how we found S. As you guys might notice, I wasn't worried about defining some like very different value for alpha and psi. I just defined values that are greater than or equal to 0 as necessary, but S was computed. Why it was computed using this equation equals 0, but making it equals S, of course, because I need to make sure that, of course, alpha, psi, and S's represent the same solution. And of course, the gap was given by this, probably remember, it's S times alpha, S times alpha. Okay? Both here, diagonal matrix, when I apply diagonal again, it's going to be a vector. And diagonal in another diagonal matrix is going to be a vector. Vector multiplied by vector, it's a dot product. And it will give the gap, the distance I have in between my primal and my dual spaces, sorry. Here, I started building up my Jacobian matrix. From the first to the 200th row and first to the 200th column, I'll have matrix Q. Take a look, matrix A, which is my Jacobian, I decided to call as A, could be J, sorry guys. It will have zeros. It will have 3 times 200 plus 1 rows and 3 times 200 plus 1 columns. So this is our first block. That block happens in here. Okay. Next, I decided to take the row from 1 to 200 and the column 201 to assign my y vector, as you guys might notice over here. Okay, my y vector. From 1 to 200 and from 202 to 401, sorry. That's my minus diagonal matrix in terms of the number of rows of Q. That's actually my minus I over here. Okay. If you do something like this in R, a diagonal of 5, it's going to be a matrix 5 by 5, which is an identity matrix. Let me use a minus sign, sorry. It's going to be minus 1. Okay. That's what I did over here. And over here we have from 1 to 200 again. That's from row 1, from the first row to the 200th. And from this point, 2n plus 2 to 3n plus 1, we're going to have a diagonal with 1s. That's an identity matrix. Second row, I just came up with minus y here. So that's minus y exactly in that second, I call it second row, but that should be second function. Okay, sorry. Why I defined those guys here? Because they're not going to be adapted. They're going to be static along all iterations. So before starting my operation, I said, okay, let's define Q, Y, I, okay? Because those are static. While my gap is greater than a threshold, you are going to do something else. You're going, of course, you're going to define my blocks depending on the third function, S and alpha over here, okay? So from 202 to 401, and from the first column to the column 200, you're going to define my matrix, my diagonal matrix S. And then from 202 to 401, from, of course, 202 to 401, you're going to set alpha as in here. And the fourth function, not row, is going to be from 402, sorry, to 601. That's in terms of rows. From the first column to the column 200 minus psi, as in here. And then here, we're going to have C minus alpha. That's all. Now we start. This is a vector B. This is actually, I call vector B as this guy. So this guy will have, of course, at the beginning, it's going to be fed up with zeros. It's going to have 2 times 200 plus 1 rows, and the number of columns is going to be 1. Okay? And here I just defined this is going to be my F1. That's exactly what happens here. My F2, my F3, my F4. Actually, here is already minus F1, minus F2, minus F3, minus F4. And that's why I've got like here's minus E, here's E, here's plus positive Q. Actually, when I apply, of course, this minus is going to be negative Q. Here the solution is the same, is ideal. Okay. So I'm doing all that. Of course, here I'm setting up the values for my vector B. So setting up the values for my vector B. And at last, oh, it's funny here, guys. Here it should be 3. I think there is a small mistake here. 3. So here I'm just defining all elements for my vector. What I call B is this guy, of course. So this is a matrix I call A. This is B. Okay. And then here is I use the solver. This solver here, I think it comes from this package, limsolve, okay? It's this solver here. And as a result, it's going to provide delta alpha, delta B, delta S, delta psi. What comes from the first to the element 200 are the alphas. Then 201 is going to be my B, 202 to 401 are my S's, and from 402 to 601, I will have my X's. Okay, so I just take all those values back, and now I decided to do something like this. I decided to change my diagonal matrix alpha, taking itself plus some eta times delta alpha, which was computed here by my solver, B in terms of eta times delta B, which is in here, diagonal matrix S in terms of eta times delta S1. Sorry for this one, guys. Can change later. And Xi, of course, plus eta delta Xi, which is in here. After updating variables, of course, eta has to be smaller than 1, okay, guys, to avoid like crossing the barriers. Could be like something like 0.1. I think I defined eta as exactly as 0.1. Okay. I didn't use like any very different strategy to define eta here. I just used like 0.1. Thought it was better. And my iterations here. My gap is being measured here. I just used me as gap divided by iteration, but this me again could be just itself multiplied by 0.9, something smaller than 1, to make possible some sort of some approximation to the barriers, the barrier term. Here I'm going to print out the gaps for you, and at the end I plot. Yeah, I'm not good with those plots, guys. I wrote some functions here to plot. You can verify later. They are on top of this. That's all my thing. Okay. It's not my lane. Test simple data set. Let's run it. So I'm going to load it. I think the name is SVM IPM. Yeah. Test linear. Oh no, it's not. Test simple. Sorry. Test simple data set. It's going to run, take a look at the gap. The gap is going to be reduced. And me, I also decide to plot, to print out me, so you guys can see what's happening with me along the iterations. The gap has to be quite small, has to be smaller than 10 to minus 5, I believe. Let's get back here. I think the threshold, I define a threshold. Yeah, 10 minus 5. So it's going to take like forever, of course. I could give like faster steps, changing me faster to approach faster to the barriers, but I'm not worried about the time I take. Just worried about the solution. This is our input space. Please pay attention. You are going to notice that we have like some red point here and some red point over there. They do not provide the best solution because of the solver we are using, but this point in red and this point in red and this in red are our support points, support vectors, along which we've got a hyperplane, a sidewalk hyperplane here, and a sidewalk hyperplane here. Some of you may ask why it's not this point. Of course, because my solver is not that good, and because I could have I could have iterated more or waited more for the iteration. When I click on top of this, you are going to see the result for the classification. What I did here is I just took all points belonging to the negative class, which are in my training set, and I gave those 100 points whose class should be -1, and those 100 points coming up later, that should be classified as +1. And you're going to see that all points should be above this, because this is my support vector, and here you can see that support vector is not the best as possible. You can see some points are closer to the hyperplane because of my solver, as I mentioned before. We're going to improve this, don't worry. That's just a way of seeing the results. When I click again, I see the results like this. This is what I supposedly had to give as answer for my first 100 points of my training set. And for my 100 points of the positive class, they fit, of course, with +1 and here -1. And at last, we can see the hyperplane where it lies on. Guys, sorry for my plots. My plots are not the best. All the plots can be seen in the functions I wrote up here, guys. Continuous classification, discrete classification, and plot hyperplane. I'm not good with those plotting things, but please take a look. The most important was actually this, test simple data set. Of course, I can change here. I can, for example, use a greater value for C. That's going to take like more time. I can use like eta could be like 0.5 instead of 0.1 just to make it faster. But this is going to make it slower. So let's see what happens. I started with 10. Here it could be like itself multiplied by 0.9, I don't know, something like this. Let's see how it's going to perform, and you can test later. You can test at home, of course. You can run it at home, define your boundary. Okay, you're gonna have some solution. At this point, we didn't have like the best solution either. The support vectors are here, the support vectors in red here, and here, take a look. Okay. So of course I have like some points closer to the hyperplane. That's why we've got like some smaller values, negative values here. And here we are just going to give like, not giving like 1 for the closest point. That's not the best solution, but it solves, but it's not the best solution. Of course, that depends on my parameters. That depends on how much I want to how I parameterize my algorithm. I'm going to leave like this gap as I did before, divided by iteration. Yeah, could be gap divided by iteration, maybe to the square to make it faster. Here I started with my C equals to 200, which is like a very large value. Here I could go like with eta 0.99 just to make it faster. Yeah, let's see how it's going to perform now. Yeah, see the result like this now. Yeah, it couldn't resolve. Sometimes happens this because this solver is not the best. We're going to use a much better solver in the next video. Let's use like 0.9 again. Let's see how it goes. It's going pretty much well. I'm going to Ctrl+C here and cancel out my plot. Actually, I'm going to try to reduce my threshold to 10 and -20 here to see how it goes. Just to verify if I'm going to get like better set. Oh, take a look at this. Again, this means probably we're crossing the per year, I suppose. Okay. But yeah, we could use like smaller eta, maybe 0.5 to avoid crossing. I should adapt it. Actually, in the next solution, it will be very, very good. You're gonna see it. Yeah, going better. Yeah, that's much better. Let's see. Yeah, it should be smaller, even smaller. Like could be 0.1 here. Yeah, let's see. I'm going to share this solution with you guys. You test it later, verify the results, see the gaps are being reduced, but not that much. Maybe I could give like smaller steps. Let's see. Yeah, let's see. Yeah, I'm just giving smaller steps. It's going to take like forever. Not nice. Yeah, we better give like a greater step over here. C could be 2, not 200, because it's too big. And let's see how it goes. Yeah, it's good enough to run at home. It's getting smaller and smaller, but not too fast. Yeah, it's kind of interesting. Yeah, to take like a long time, but it's fair. Maybe here I could just increase this a little bit more. Maybe like 0.1. Yeah, let's see how it goes. I think my threshold is too small for this solver. This solver doesn't have like such a what's the name for that? I forgot. Such a precision. Okay, it's running. Yeah, of course, with 0.1 here, it's going to take more time. But it's good. Good to have like some patience and see the results, like see it converging slowly. So guys, that's all we have in this video. Just going to wait here and see if we find something smaller than 10 to minus 5. We can, yeah, 10 to minus 6. That's really nice. Let's see. Oh, to minus 7. Perfect. Let's see. Minus 8. Wow. Sorry, guys. Yeah, so I'm going to change this to minus 7. So if it goes like to 10 to minus 7, it's going to plot something as the final result. Now let's increase a little more of this, 2.2, my eta, to adopt my gradient descent method, just to make it like a little faster. Yeah, the next solution will be really, really fast. You're gonna see. We're gonna use a package that's called low rank QP package. And on top of that, we're going to discuss like a bunch of possible solutions. Oh yeah. Yeah, but unfortunately the solution is not that good either because of the solver. So we are finding this point as a vector, a support vector, and this is a support vector. This is better. Again, classification, again. Yeah, the hyperplane. Guys, we see you guys in the next video discussing on the really, let's call like full and professional implementation of the support vector machine, even supporting hyper kernels. Okay, see you.